the first thing I want to say about the test is, you know, uh, I don't put grades on these or anything. I just think of it as kind of a percentage, and compare the percentages to roughly to the ABC scale in the syllabus. And um, don't worry too much about points on one test. I'd be happy if you think I misgraded something, missed something you wrote. I'd be happy to talk about it. But um, really, the main thing that I want to say is if you had like a really low score on the test, please come talk to me after class or in office hours or send me a message. This is all stuff that can be straightened out. But if we don't straighten out this early stuff early, it's going to just keep going through the whole class. So I don't know. So say somewhere in that 50% range or something. If you had a score down in that range or below, let's just get it straightened out as quickly as possible. Okay. Um, okay. So I'm going to do 3 questions from the homework. And a lot of these are cases where you're given motion, like the motion that's described is described in a non-inertial coordinate system. Either the coordinate system is, well, we're not doing rotating coordinate systems yet. So all it means to us so far is that you're given information, but it's in an accelerating coordinate system. Well, you can't use measurements in an accelerating coordinate system in Newton's second law. So what you have to do is use relative motion to figure out what the measurements would be in an inertial coordinate system, and then you can use those corrected accelerations in Newton's second law. So this is an example of that. Let's describe what's going on. So we have a big Ferris wheel. It has a radius of 4.5 meters. It rotates with a constant angular speed of 1.2 radians per second. And it doesn't tell us which direction it's rotating, I guess. I'll make it go counterclockwise. Since it's constant, there's no angular acceleration. And it's mounted to a train car. The path of the train car is perpendicular to the plane of the Ferris wheel's circular motion. Okay, so the plane of the circular motion is the page. The train is moving perpendicular to that, so it would look something like this. I'm not like a great drawer of train things, but okay, there's the train, and we're going to say it's accelerating, well, into or out of the page. Our coordinate system is like this, X, Y, Z coming out. And I'm going to say, so it could be rotating this way or this way, right? I chose this way. And the train could be accelerating into the page or out of the page. I'll choose this one. So those are both just arbitrary choices. Actually, the direction it's rotating is not going to affect the acceleration, but the direction that the train is accelerating will. And so I sketched the system, and now say we have a passenger here. We want to calculate the net force applied to that passenger by the net force, all the forces acting on. That would be the sum of gravity plus any contact forces applied by the seat and stuff like that. So this is the system. And now for the acceleration of the passenger, we want it relative to the ground, okay? Calculating the acceleration of the passenger relative to the train does not work in Newton's second law. We get wrong answers for the forces. So we want the acceleration of the passenger relative to the ground, and that's the acceleration of the passenger relative to the train plus the acceleration of the train relative to the ground. The acceleration of the passenger relative to the train is just circular motion. So what equation am I going to use for that? Yeah, watermelon equation. So this is alpha cross r plus omega cross quantity, omega cross r.
And the left-hand side of the equation is 0 because there's no angular acceleration.
Yeah, that left term, right? So angular acceleration is 0. Angular velocity, the way that I drew it, so use the right-hand rule.
It'll be the z-axis, right?
Yep, the way I drew it, right-hand rule says it's in the positive z direction. The magnitude is 1.2, so 0, 0, 1.2. And then r, this has a radius of 4.5. Think of the definition of the r vector. It's from the center of the circular or spherical motion to the point we care about. So that's the negative y direction. So that's 0, negative 4.5, 0. And so this is 0, 0, 1.2 crossed with the quantity 0, 0, 1.2 cross 0, negative 4.5, 0. Okay, so this is a coordinate system fixed to the train. That's not inertial. So we can't work with this yet. But now we're going to use relative motion. So the acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the train. That's what we just figured out. Plus the acceleration of the train relative to the ground. And so that is 0, 6.480.
And then the acceleration of the train also to the ground is 2.5, as stated previously, right?
That's right. So it says that it's speeding up at 2.5 meters per second squared. I said that that's in the positive z direction. So 0, 0, 2.5. And so the acceleration of the passenger relative to the ground is 0, 6.48, 2.5. And so now we can go to Newton's second law. We're just trying to calculate the net force. So all we have to do is multiply this by the mass. The net force is equal to the mass of the passenger, 50, times 0, 6.48, 2.5. And so that net force vector is 0, 324, 125 newtons.
acceleration of the train with respect to the ground was given, right? The 2.5?
Yes, that's right. It said it's speeding up at 2.5 meters per second squared. So it could have gone, I could have had it going into the board or out of the board based on what it said. It didn't give enough details. So I chose it to be going out of the board.
Okay.
Any other questions about that one? Yeah.
Give us that other acceleration.
The 2.5?
Yeah.
Yeah, the 2.5 is right here in the, so speeding up at 2.5 meters per second squared.
And for the,
Oh, one other thing. It says it's speeding up at 2.5 meters per second squared. What direction is the velocity vector?
if it's speeding up, that means it's going in the same direction.
Same direction as acceleration. So if my acceleration is out of the page, it means the velocity also is out of the page at this instant. That didn't come into the problem, but
When you were talking about the inertial coordinate system,
Yeah.
is that like we can't use coordinate systems for like the reference point is moving for the Newton second law?
yeah, think of it as like all kinematics measurements are taken by a video camera, and it's like what that video camera is mounted to. So in this case, think of all these measurements as being taken. So when I say a video camera, have you ever seen like
Can we watch the video again?
yeah, no. That we should do a semester where all we do is watch Jamiroquai and see if you learn the same amount. Have you ever seen like for making like sports video games or for sports calculations and stuff, they put all the reflective markers all over people, and then video cameras are constantly taking measurements of where all of those are. So think of a video camera like that, that's always taking measurements of everything, locations. And from that, it's saying in its reference what it sees as a velocity and what it sees as an acceleration. So if that video camera is mounted to something that's accelerating, you can't use that information. Okay, and in the relative motion subscript notation, what the video camera is mounted to is always like the denominator of that, it's that lower subscript. So in this case, we use circular motion to calculate the acceleration of the passenger relative to the train, but that means that this acceleration that we calculated is what a video camera would see that's mounted to the train. That's not good enough for us because the train is accelerating.
And what if it was at a constant velocity?
That's fine. Yep, that's totally fine. It would get differences in velocities of things, but it wouldn't measure differences in accelerations of things. So we can use that exactly the same. So if the video camera was on a train going 100 miles an hour or whatever, it would still measure this same acceleration, relative acceleration. And then we could use it the same way.
But if the problem was asking for like a specific velocity, we couldn't do it then because the velocity values would be different.
Exactly. Right. Exactly. Yeah. So there is no true velocity in the universe according to classical physics. There's no saying whether we're sitting still right now or moving at 1,000 miles an hour or whatever, but there is a true acceleration. So, yeah. Actually, that's in relativity, it's a little bit of a different story, although it's the same story for things that aren't moving close to the speed of light. But according to relativity, physics can tell you what a true velocity is. But the differences between even still and 1,000 miles per hour are minuscule because it's all dependent on like a ratio of the speed of light, which is 300 million meters per second, really fast. Any other questions about this problem? Okay, so everything that we're doing in this class, I don't know if I really ever said that, but everything that we're doing in this class is classical, is using classical physics. And classical physics works perfectly as long as things aren't getting close to the speed of light. But if things get close to the speed of light, you need to approach them differently. So now number 4. So you have these two carts. There's the 100 Newton force applied to the left. First, it asks what's the acceleration vector of the whole system. Then it asks for the velocity and position as functions of time, and then some force vectors. I'm going to do A, C, and D first, and then we'll talk about B. That's a differential equations thing. So if we're going to calculate the acceleration of this whole system, the easiest way to do that is to isolate the whole system at once. Okay. And then you just have a single object, a single force, and you calculate the acceleration. Or we could do A, C, and D kind of as a single problem. Let's do that actually, because I think it's kind of a good habit to get into for the stuff that's coming in dynamics. So I'm going to do a free body diagram of the 50, use Newton's second law, free body diagram of the 75, use Newton's second law, solve it as a system of equations, and then our answers for A, C, and D will all be sort of given in there. So a free body diagram of the 50. The weight acts at the center of mass. So 50 times 9.81 is 490.5. There's a pushing force from the ground. I'll call that N50. There's the given 150 Newton force. And then the only other place where the surroundings make contact with the boundary is where this touches the 75. That's a pushing contact. So it's perpendicular to the surface, toward the chosen body. Give it a name. And that's it. So Newton's second law says 150, 0, plus 0, N50, plus 0, negative 490.5, plus negative R0 is equal to the mass times the acceleration. This thing is not going to jump off the ground or sink into the ground. We're going to assume it's just rolling horizontally, so I'm going to put this as A0. The second equation tells us N50 is equal to 490.5, but that's not something that we're asked for. The first equation says 150 minus R is equal to 50A. We can't solve that because it's two variables, so I'll just set that aside. And now I'll go to the 75. The downward force is 73.575. There's a pushing force from the ground. I'll call that N75. There's nothing happening on the right side.
It's supposed to be a 735.
What did I put? Oh, yeah. Right, thank you. There's nothing happening on the right. Over here, there's the contact with the 50. It's a pushing contact, so it's toward the chosen body. And it's a Newton's third law pair. It's just two things pushing on each other, so I have to give it the same variable I gave it up there. So Newton's second law says positive R0 plus 0, negative 735.75 plus 0, N75 is equal to the mass times the acceleration. And since these things are moving as a single object, it has the same acceleration as the first one. So N75 is equal to 735.75. But then the one we want is R is equal to 75A. That's another single equation with two variables, but now we can solve the start equations as a system of variables. I'll substitute the second equation into the first. You could always do reduced row echelon form to solve this, but usually it's a little faster if you have two equations to just do it by substitution. So we have 150 minus R, and R is 75A, is equal to 50A. So 150 is equal to 125A, and so A is equal to, that is 6 over 5, so 1.2. And that's not an acceleration vector. That's just a variable value. But we've already said that the acceleration vector of each of these is, we already specified this is the acceleration. All we have to do is figure out what A is. And so now you can plug it into that, and you get that the acceleration vector is equal to 1.20. And now for the force on the 75 by the 50. Well, this is the force on the 75 by the 50. We just have to plug in the R value we got. Oh, I haven't calculated R yet. I'll just put it in here. So 75 times 1.2 is 90. So the force vector on the 75 by the 50 is 90, 0. And the force on the 50 by the 75, we could go up to this equation, and this is the force on the 50 by the 75. Or we could just recognize that it's a Newton's third law pair and it has to be equal and opposite to this one. Either way, you get the same answer, negative 90, 0. Anybody have any questions about that one? Oh, and then there's still the differential equations thing. So we're given the position at 1 second, the position at 3 seconds. What are the position and velocity vectors? Well, this is actually a little bit of an interesting one, because notice we're more used to having boundary conditions, one boundary condition for the position at a given time and one boundary position for the velocity at a given time. This gives two at two positions at different times. So okay, let's go through this. Well, all we have to worry about here is the all we have to worry about is the x motion. Notice that the y motion just stays 0 and we don't have any acceleration in the y direction. So we can just make this a problem involving x just to save a little time. So what we have is that dv dt, that's the acceleration, is equal to 1.2. And so dv is equal to 1.2 dt. Integrate both. And you get that v is equal to 1.2 t plus some constant of integration c1. And normally we'd be able to use a boundary condition here, but we don't know any boundary conditions for velocity, so we have to, let it ride. So now dp dt, or dx dt, is equal to 1.2 t plus c1. So dx is equal to 1.2 t plus c1 dt. You can integrate both of those. And you get that x is equal to 0.6 t squared plus c1 t plus a new constant of integration, c2. And now we have our boundary conditions. So first of all, it says if you plug in 1 second for time, you get 0 for p. So the position is 0 when all the t's are equal to 1. So we have 0.6 times 1 plus c1 plus c2. And then the second boundary condition says when time is equal to 3 seconds, the position is 5. So 5 is equal to 0.6 times 5 squared plus 5c1 plus c2. And I'll write this as c1 plus...
It's supposed to be 3 squared plus 3c1.
What?
Yeah, isn't it?
Aren't those 5's 3?
Did I...
It equals 5, but the t's are 3.
Yeah, time 3 and then position 5 instead of time 5 squared.
T3
Oh,
equals 5.
yes. Thank you. Okay, so the time is 3, the position is 5. 3 squared, this should be 3. So c1 plus c2 is equal to negative 0.6. This one says 9, so 5.4. So we have 3c1 plus c2 is equal to negative 0.4, I think. And I'm just updating my function. So 0.6 t squared plus 0.1 t minus 0.7. And now that we know C1, we can write our expression for the velocity too. So the velocity as a function of time is equal to 1.2 t plus 0.1. So if you wanted these then as vectors, we have the position vector as a function of time. That's this thing for the x component and 0 for y. And here the velocity is 1.2 t plus 0.1. That's the x component and 0 for y.
Why do you use xt and then et?
I don't know. Yeah, those are interchangeable to me.
Okay.
But I mean, so this would be like, I think of the single components as x, y, and z, I guess, but the vector I call p.
Oh,
I guess that's why.
okay.
But some people you'll see use x vector as the position vector.
Oh, I see.
Yeah. So just think of those as interchangeable, I think. You know, there could be a problem where, like, you could put all this stuff together. Most of this problem was just kinematics, you know. But you could make something where, like, the coordinate system is moving along a circular path, and then the camera that's fixed to that thing is tracking these objects as a function of time, and you'd have to use circular motion and relative motion and differential equations all together to get this thing. The trick is, so it can be a lot of stuff, but really it's only just layers or overlapping of like 3 possible things. We've talked about circular and spherical motion, relative motion, and differential equations. And you just have to be able to identify when this is coming into it, you know? Yes?
So for this part B of the problem,
Yeah.
use the acceleration that we got from the previous part.
That's right.
Is that the only way to solve it, or is there a way to solve like part B before?
Nope, you need the acceleration first, because there's no, otherwise you just don't have, I mean, you could say it's a constant and solve it as a constant and then go back and plug it in later, I guess, but you can't solve it until you use the kinetics to figure out that acceleration. Any other questions? Okay, one more. Okay, so this one I made you do something talking about friction. I'm not really planning to talk about friction in this class, so you would have to use your friction information from Physics 1. So we are going to use a coordinate system like this. And I'm going to, okay, so in this coordinate system, you know, the usual coordinate system, the weight of the 15 kilogram box is 15 times 9.81. So that's, 0, negative 147.15. And so what would it be in that red rotated coordinate system? Let's use a rotation matrix for that. So we have, so we're going to go from this to this. It says that that incline is 30 degrees. So is that's going to be a rotation about the z-axis. Is it going to be a positive 30 or a negative 30?
Negative.
Negative. Yep. That's a clockwise rotation. So, and your thumb is pointing into the page. So this is negative 30 degrees about the z-axis. And so we're just going to multiply, our q is cosine of negative 30, sine of negative 30, 0, negative sine of negative 30, cosine of negative 30, 0, 0, 0, 1. When I brought this up before, did I do it as a 2x2 matrix or a 3x3 matrix? Okay, I did. Okay. So, since all our rotations are about z, you can also do this as a 2x2. But so this would be 0.866, negative 0.5, 0, positive 0.5, 0.866, 0, 0, 0, 1. And we're going to multiply it. So our mg in the new coordinate system is that Q matrix times 0, negative 147.15, 0. And something went wrong. 1, 2, 3. 1, 2. Okay. 3. All right. And so you get 73.575, negative 127.432, 0. And then in a standard coordinate system, the weight of the 8-kilogram box is 0, negative 70, 78.48, I think, 78.48, 0. And so in the new coordinate system, again, that's that same Q matrix times 0, negative 78.48, 0. God damn it. Q. And you get 39.24, negative 67.960. Okay, so when we need those weights, that's what those are. Oh, and might as well do that 100 too. That is that 100 Newton force. In the standard coordinate system is negative 100, 0. So in the new coordinate system, that is Q times negative 100, 0, 0. And that is just 86.6.50, negative 86.6, negative 50, 0. So anyways, when you have all that stuff programmed into your calculator, it's a lot faster than doing the trigonometry of everything. So now a free body diagram of the 15. We have a weight force down of 147.15. We already know what that is in components, but I'll write it like that. And we know that these boxes are sliding down the incline at the instant shown. That means that the friction force is up the incline. So we have like an N15 here. We have a friction force up the incline of 0.2 times N15. And then we have a contact force, it's a pushing force. I'll write that as R. Any questions about that first free body diagram? So Newton's second law for this one says negative 0.2 N15 plus 0 N15 plus the weight force, which we have up here, 73.575.
Does the 147.15 right? The weight force.
No, we converted it to the coordinate system.
Yeah, so we're in this new coordinate system now, so it's this one, 73.575.
So instead of having just like one horizontal or vertical component, has two now.
On both.
Negative 127.432. One, two, three, and then we have negative R, 0. And this is equal to 15 times, this thing only accelerates along the x-axis, so I'll just write it as A0. The signs will work out on their own. I just noticed that I multiplied this wrong. No, that's right. Okay, that's right. So N15 is equal to 127.432. And then we can plug that into the first equation. So negative 0.2 times what N15 is, plus 73.575 minus R is equal to 15A. And so we have I'll write it as, I'll get all the variables over on the right side. So we have R plus 15A is equal to 48.09. So that's our first equation. And then we'll go to the 8 kilogram. So we have 78.48 down. We have a normal force N8, a friction force up the incline of 0.2 N8. We have a contact force from the 15, like that. And then we have the 100 Newton force that's horizontal. Any questions about that? So Newton's second law says, so we have a bunch of stuff that's parallel and perpendicular to, the incline. So those are easy in our new coordinate system. We have R0, negative 0.2 N8, 0, 0 N8, and now we have the weight force. So 39.24. Negative 67.96. And then the 100, I have one too many here. This should be negative 86.6. So negative 86.6 and negative 50. And all that is equal to the mass times the acceleration vector, which is the same as the first one. The normal force this time is not just equal to the weight component because we have that other force in there. So this is equal to positive 117.96. And then we have R minus 0.2 times 117.96. Plus 39.24 minus 86.6 is equal to 8A. So I'll write this as R minus 8A is equal to positive 70.95. And that's our equation 2 star. And then I'll solve that by reduced row echelon form. Okay, new. And I got that R is 63 exactly. And A is negative 0.99. So the acceleration, it's in the negative x direction. So that means it's up the incline like this. And that R force, I mean, so this is the acceleration vector, 0.99 meters per second squared this way.
So it's slowing down.
So it's slowing down because its velocity was down the ramp. Exactly. So the angle wasn't big enough to overcome the friction. And then if you wanted specific, I don't know if it asked for specific vectors. Yes. So what's the force vector applied to the 15 by the 8? Well, go to Newton's second law for the 15. And this is the force on the 15 by the 8. So the force vector on the 15 by the 8 is equal to negative 63, 0. So the force on the 8 by the 15, Newton's third law says that's positive 63, 0. Any questions about that?
How did we know that the acceleration was only on the x direction? If we want-
Yeah, because so anytime something is rolling or sliding along an incline, we're going to assume that it's not bouncing up off the surface or sinking into the surface, and so it's constrained to move along the x-axis. And we didn't know whether it was the positive x or the negative x, but that sign will work out on its own as long as we restrict it to the line that it can move along. Basically, that's just a constraint that says we're assuming that it's only going to move along that line. If this was made out of, if that was quicksand or something, then we couldn't make that assumption. It would be able to sink in, or if it were bouncing, we couldn't make that assumption. Yeah.
So when we're using the like transform matrix to transform the dies, were we transforming it into a coordinate system that was like parallel with the slope?
Yeah. Let's see. Where did I draw it? Yeah. This is the coordinate system we're assuming. So the x-axis is along the surface and the y-axis points straight out of the surface.
Okay.
That's the one that you always used in physics 1. Any other questions about that? Yes.
So how do you know that the angle is negative 30 and not positive 30?
Yeah, because it's a right-hand rule thing. So we know that both of these coordinate systems have the z-axis coming out. Okay, so you just have to think, am I curling my fingers this way, which would be the positive z direction, or this way, which would be the negative z direction?
Okay.
And I had to do it 30 this way, so that's the negative z direction. I could have gone all the way around. That's fine. And so then it would have been a positive rotation of 330 degrees. And that would come out with the same numbers. Any other questions? That rotation matrix stuff isn't anything that you'll need to use in this class, but it is a super handy tool in mechanics. And if you take deform from me, we'll talk about it a lot and use it a lot. Okay. Well, let me introduce this and see where we are with time. The next thing we're going to talk about, so we're going to talk about 2 more cable and pulley topics. These are both going to be short. The first one is pulley advantage.
Like a tier 1 mechanical advantage or a 3 advantage?
Well, yeah, we're just going to talk about the principle of it, and it applies, you can apply it in a lot of ways. But the idea of pulley advantage is this. I remember when I took my first physics class in high school, I was surprised to learn that all a pulley does is change the direction of a force, because my parents, who are stupid, were always telling me that, like a pulley can reduce the amount of force you have to apply to lift something. Okay. So I just didn't get the connection. Actually, my dad is like the smartest person in the world, but he not very good at physics. Okay. So if you have so let's say if you have whatever weight here, the weight that's required to hold this weight still is mg. That pulley isn't doing anything to reduce that force. All it's doing is changing the direction of the force that you have to apply. Okay? But there is a way to rig combinations of pulleys. So let's think of it like this. So let's say we have one pulley here that's supporting the weight mg. And a cable is going underneath that hanging pulley to support it. And then going over another pulley here. Pretend that's vertical. So in this setup, what's the force that you have to apply to lift this?
Half of mg, right?
Right.
That's because one cable is putting the way
Let me just finish talking about this. So it's not the pulley that does this. All the pulley does is change the direction of the force. Okay. But this combination, you can rig up pulleys in such a way that the force required to lift this thing goes down. Okay. And so we're going to go through the calculation of why that is. And what? Oh, I thought you were. Okay. So we're going to talk about why this works, and we're going to do it in dynamic calculations rather than this is just a static calculation. Okay. So we'll do that next time. And then the second thing we're going to do is we're going to put this pulley stuff into what's called an Atwood machine. And it gets at a little bit of some stuff that comes up a lot in relativity, actually. So here's what we're going to do now. We're going to think of that these pulley systems are not connected to a non-accelerating ceiling, but instead they're connected to the ceiling of an elevator. Okay. So we could have one like this, supporting this MG. Okay, but this has a acceleration one way or the other. It could be either. The answer changes based on that. And then, I guess just because I have two pictures above, I'll draw it here too. You could do similar things with a block and tackle system. Where this is accelerating either up or down. And we're going to calculate the acceleration that an observer would see in this, given different forces on the left and right. And what you would see is that acceleration of the elevator leads to differences in the behavior. And so the relativity thing that comes up is that there is no way to determine whether you are in an accelerating coordinate system or in a gravitational field. So any acceleration could be explained by maybe sometimes a very weird gravitational field, but by a gravitational field. And we're going to see that here. So like, for example, if this elevator is accelerating up, it's going to behave exactly as if gravity was a little stronger than it is. And if it's accelerating down, it's going to behave exactly like gravity was a little weaker than it is.
It's the same thing.
So, yeah, I think maybe relativity people would say it's the same thing. Gravity and acceleration would say it's the same thing. I don't know, because I'm not a relativity person. To me, I mean, I'm just going to say they act the same, But like, okay, like you're living on a planet and there's a gravitational field that seems very much to act like all of these forces are going right towards the center of the planet, and you're going to try to tell me that's actually an acceleration. Come on, bro. No. Yeah, right. Yeah, maybe. Yes. Question?
I was just remembering how all like the explanations was always like, oh, you're accelerating on like again. Through pure space time or something. So
Yeah.
technically,
Right. I'm going to very, very, very quickly get out of my ability to talk about relativity. So no more questions. Okay. Questions about classical physics only.
Atwood machine, is that just like a box that accelerates with like this pulley inside of it?
Yeah, right. Yeah, kind of like that. I don't know. It's just called an Atwood machine, but it's really kind of just like a concept that explains where we'll go through the calculation and see how that acceleration affects the behavior. And more than anything, it's just a way, it's another step for us to practice layering the relative motion equations along with kinetics. Any other questions? Okay, that's all for today. Goodbye. You successfully prevented me from asking you any more homework questions for Wednesday. Good job.
Did you just brought up?
Yeah.
So